Okay, radio fans, it's K8BYP with a demonstration of why I went through such misery to restore this high-end HP and Tektronics test equipment. The job, after having wound filament chokes, got a box, 2 filament chokes, got a plate inductor for the vacuum tube amplifier, have 2 high voltage chokes, got the RF filtering capacitors for the power supply just before this inductor, after the plate chokes, and the plate, the output coupling capacitor bank made of doorknobs. There's one thing that's got to be done to make sure the tube is not turned into ashes, and that is all these components need to be sweep tested up to probably about 200 megahertz. I did some testing on my low frequency equipment, the fairly inexpensive but nice AWG, and my old service scope. And the results I got for this choke, for example, that deviated from pretty much dead flat at 50 dB down, changes in the stop band were mainly because this was too close to the table. Well, now it's up and away and testing at lower amplitudes. So that testing wasn't quite reliable. But with this very high dollar laboratory equipment, a 500 megahertz scope, and the HP microwave generator, and I'm going to pull that away from the wall just a touch. Make sure the cooling fan has airflow. So the generator is set to 1 megahertz, or to us old timers, 1 megacycle, with a sweep width of 50 megahertz. And that's going to test a sweep up through 6 meters. Normally, this kind of testing might be done with a micro strip line. I've showed you that testing in previous videos on the networks. But here, since I'm dealing with mainly chokes, which should be an open to RF, I've come off the RF output port through a cable BNC into the 50 ohm scope. Good 50 ohm match. The choke is off to the side on the T port. If it's an extremely high impedance, in theory, the system will never see it. Normally, we would never do this, because this would, if we did this with a 50 ohm load here, that would be 25 ohms and a bad mismatch and reflection back into the generator. But the rationale here is that since this is supposed to be an open, it doesn't matter. So we'll punch the old sweep button and we'll start sweeping. The amplitude is 2 divisions, and we're looking for any significant deviation from that, like a sudden drop in amplitude or a sudden increase, I guess. I swept this without the choke, got up to 200 megahertz, got about half of a minor division deviation. There's a drop just a touch. Okay, no funny responses there. So let us clear keyboard, 50 megahertz center frequency, sweep width 150 megahertz sweep width, and now we'll go to VHF, almost UHF testing. Okay, here we go from 50 to 150, or 50 to 200. The beauty of this over digital instrumentation is that it misses nothing. It's a continuously changing frequency sweep down to a fraction of a cycle. So no matter how narrow the resonance might be, this will find it. Digital units that use FFT processing, you got to have a few tricks up your sleeve to accomplish that with an FFT box. You got to change the sweep parameters, get multiple sweeps. because of the sampling. So smoothly. Let's do it again. I thought I saw a little trace distortion. Maybe not. I was looking on the upper, excuse me, the upper left of the trace, and I thought I saw some. Maybe not. Apparently not. Might have been something in the phone. Now this is only testing at about, the generator set on 3/10 of a volt. That's about a 1 volt amplitude. Then this shows no strange behavior whatsoever. So I'm going to take that off and solder on one of the plate chokes and then the big plate inductor and test them. These components can test perfectly, be put in an amplifier and cause all kinds of problems because suddenly in the amplifier they're exposed to much higher RF voltages, and those can couple to a chassis wall. So if that filament choke, I'm intending to put them in against a flat shield wall, that's going to cause capacitive coupling. Once it's installed in the box, then I'll have to sweep it again to see if it did anything weird because of straight coupling. So this gets rather complicated. And now with the plate choke, let's do a sweep from 50 to 150 megahertz. Where is my sweep? Where's my display? Okay, the volts per division control's noisy. Okay, here we go. Looks like a little roll off in amplitude. Still changing. Still changing. There, it stopped. And now for the 1 to 50 megahertz range. Now, why couldn't the choke be put in series with the RF transmission path? Get a strip line, cut it, soldered in line. That's common test equipment. That would open up the 50 ohm load for the generator and give it no load. These high-end instruments expect to see a load of their characteristic 50 ohms, nothing else. The 651 could go 600, but it has to be matched. And now the BHPI, big honkin' plate inductor. And by the way, this inductor looks like it's awfully big, but it replaces that big monstrous choke or inductor. It replaces that. See how much smaller the toroid is? And what's wrong with this is just a solenoidal form inductor on a ceramic form which has extremely high dielectric properties. I think that's it says 1000 microhenry. That's for 4-1000 amps. See, it's a single space wound. But nothing in this conserves magnetic fields, and the fields will spew all over the inside of the cabinet. So this is what you call dirty. And that straight coupling's got to be accounted for in checking for neutralization and for oscillation. Okay, so plate inductor sweep. Here we go. This is the low end, 1 to 50. This is sweeping through the operating range of HF up to 6 meters. The reason I'm doing this in 2 steps is that the low frequency response might relate to harmonics. The high frequency responses are probably going to be associated with parasitics. And the high frequency responses are the ones that break into parasitic oscillation and destroy the tube plate or melt the tube envelope. And that glass envelope can get extremely hot and melt with parasitics at VHF or UHF. The tube's good to 110 megahertz. It'll probably exhibit some gain above that. But the critical factor is the Barkhausen criterion, which says that oscillation occurs with a gain of 1. So if the tube gain goes really low, with some miscellaneous losses in the feedback path, at some frequency where that gain is declining, it can bust out in parasitic oscillation. Okay, here we go. Oh, yeah, the plate inductor sweep. And it looks like a slight dip in the response there. At what frequency? There was a dip. I have to go to manual sweep to find out where it is. A little dip there, then back up. Now the thing didn't go shorted, but the magnitude went down. That suggests going towards a resonance. So to find out where that's at, we'll grab manual sweep, and we'll start manually sweeping until that amplitude dips. There's a dip at 76.1. So we get us a piece of paper and we write these frequencies down. And we start sweeping up again. It's stopping at 125 megahertz. And there's a dip at about 112.7 megacycles. And need to re-enter the sweep width. Something's not right. Okay, now we're seeing some anomalies. There's a dip-de-doo right there at 133.8. Now let's see if it's because it's resting on a cardboard box. When I go to touch it, what happens? Ooh, it didn't like that, did it? Let's put a pencil through it and see if it goes crazy. No, I pick up the core and move it away. And there is a response there. So if I touch it and couple the energy into my hand, it goes away. So there's a undesirable response right there. Whether it'll result in an oscillation, who knows? Okay, now I'm going to repeat it at 1 to 50 megahertz. There's 30. And there's a response at 36.8. All of those frequencies, 36.8, 133.8, 112.7, and 76.1 are way far away from where this amplifier will operate at 3.8 megahertz. So there's nothing funny down near the operating frequencies. So that's tested everything except the transformer. I've gotten some experience with these new cores. So next is to wind the input transformer. Also got to test the capacitors. I'll have to put them in series. So that goes to show how superior, light years ahead, this equipment is from that cheap 60 megahertz buzz box and my high impedance, high resistance service scope. But this rack of equipment here was basically so expensive only the government could afford it back in the 80s. Now it's pretty much a dime a dozen. But that's what I went through all the heck and misery for to rebuild this stuff, and it works beautifully. So there's the process. KBOIP did it.